Hi, I'm Krishna Kumar from the University of Texas at Austin. Coming up next on the summer school, it's machine learning and AI in geotechnical engineering. Hello, welcome to the ASCE Geo-Institute Summer School 2025. I'm Krishna Kumar. I'm an assistant professor at the University of Texas at Austin, and today we will be looking at machine learning in geotechnical engineering in our summer school. I want to say that this is going to be an online course material. You will be able to find the course online on the GitHub site, KKS32 Courses, AI Geotech, or you can scan the QR code with a lot of the notebooks that we are going to go through, do some activities together. They're all available publicly and you can try it out. You should be also able to check out this link on the description below in the YouTube channel. All right, let's get started. Talk about AI, machine learning, and deep learning. And we've always used these words interchangeably, but let's disambiguate them a little bit. Whenever people are talking about AI, I know since ChatGPT came into the world and we've been almost synonymously using AI to mean ChatGPT, but it is only a small subset of a tool that artificial intelligence encompasses. AI is about building intelligent machines and programs that can creatively solve human level problems. Of course, ChatGPT fits very well, and that's why we almost end up calling it as an AI. But what we would normally say as a general purpose AI or a general AI or AGI, artificial general intelligence, personally, I don't think that's going to happen, at least in the next few years, but we shall see. Machine learning is actually a subset, and this is what we predominantly use in geotechnical engineering. So I want to go through some of the machine learning techniques with you today and see how machine learning models are built, how can we leverage them in building our geotechnical engineering and utilizing for geotechnical engineering problems. Then we have deep learning. Deep learning is basically a subset that came about when AlexNet came out and we were able to identify who's in your picture, whether a picture is a cat or a dog. All of those are done by what is called as deep learning. We will build our own deep learning neural network today to solve some of the geotechnical problems like 1D consolidation, for example, or even do a simple classification problem and see how they work. All right. Big disclaimer, although I work quite a lot on AI and machine learning, I want to say that it's not a magic bullet. Although many times we treat it as such, there are some big gotchas that machine learning have. What I generally dislike is that it's a big black box model. You can't really understand what's happening inside of it, and we need to be able to open up that black box and see what's happening. So for example, we may put in a set of input parameters like density, aspect ratio, porosity, a slope angle, and figure out how far this particular slope is going to run out. And that only tells us like how far it runs out, whether it's interpolating or extrapolating. We don't have any ideas. Is this correct? What is the uncertainty around the estimates? All of those are missing when I'm trying to use a black box like neural networks. And mainly because neural networks are purely data-driven, or most of them are data-driven. We will be looking at some physics-informed neural networks, so get excited about coding some physics into your neural networks today. And before we get to do that, we want to understand that the neural networks are very good function approximators. What I mean by that is given a set of bunch of data points, what it does, it fits a nice continuous function through it. And we want to make sure that the neural network is always interpolating within those function spaces on which it was trained on. When you extrapolate, go outside the training range, things started to fall apart. When you're interpolating it, everything is fine. When you start to extrapolate, things start to fall apart, and that becomes a huge issue in machine learning. So one main problem is black box. There are methods which allow us to explain what's happening. We'll look at least one of them and see how to code it up and evaluate it. And the other is the extrapolation issue. And this is a serious issue because we never get to know what these models were trained on. The same thing will happen if you try to use ChatGPT and it has no idea about a particular geotechnical principle. It's going to make stuff up. And that, in those terms, are called hallucinations. So if we plot all the machine learning models, AI models along two axes, one is called the interpretability, like how explainable my model is and how complex it could get. And typically that's the vertical axis. The more complex models become more accurate, but they lose the interpretability. Very simple classification rules type models are really good at interpretation. But as you go more and more, like support vector machines, random forest neural networks, they become extremely complex to use, to train, and we lose the explanation. Ideally, the world needs to be going towards this orange star on the right-hand side. But what happens is we've always been driving for more and more accuracy and more complexity of the model and losing the interpretability side of things. So most important thing which I want to emphasize is always try to make sure your model can explain certain physical behavior or tied to some physics like we will do later today. So we're going to start off with a simple example. I'm going to walk through what I'm going to do, and then we're going to jump straight into coding. So get your hands dirty with some Python, and I'll provide some Google Notebooks directly. You will be able to click through that link and try it out with me. So one of the first example is the example that is done on lateral spreading. This is done by Professor Raji at University of Texas in Austin. We're going to use that as the base example, their data set, which is published on DesignSafe. You're going to fetch that data and then start working on building our first AI model. So what we are trying to do is predict lateral spreading, and we're going to do a very simple case that whenever the observed lateral displacement is below 0.3 meters, we are going to say there is no lateral spreading, and if there is above 0.3 meters, we are going to say yes to lateral spreading. So all the green is no lateral spreading, and any other color, the yellow, orange, and red, we are going to club them all together and say there is no lateral spreading in that case. Okay. That's the model we're going to build. We are going to start off by building a very simple decision tree. Then I'll walk you through how to build an MLP, multi-layer perceptron, or it is also called as artificial neural networks. And then we will do more complex stuff as we go along. Okay, whenever we want to predict, we have two things. So we've seen what to predict. That is, we want to be able to predict what the lateral spreading is. Now we want to be able to say what the input features we want to use. Here, I'm going to keep things simple. We're going to start off with just four geometric parameters, or mostly topographical features, like elevation, how high a particular site is, what is the slope angle, which is how steep or shallow that particular slope is, and groundwater table, which is how deep the groundwater table is from the ground surface. And PGA relates to what is the peak ground acceleration that particular site experiences. Let's walk through a little bit of these to understand how these features can play. For example, steeper the slope, the more likely it is going to run out for a longer distance. Groundwater table being close to the surface means it's highly saturated, more open to lateral spreading. And also we expect high PGA, high acceleration means a lot more chances of failure. Okay. So how does the distribution of the data look like? And we can see that it's quite a mix. So there's no easy separation between these features. For example, if you look at groundwater depth, I can see most of the cases can have similar groundwater depth, and sometimes it has lateral spreading, and sometimes they don't experience lateral spreading. So it's going to be a hard data to classify, but let's try using some of these features. And in this case, we are going to use just these topographical features with the PGA and see how well our model is going to work. We're going to start off by building our first decision tree model. Decision tree is the most simplest of the structures. So we'll start off by creating a particular category, let's say slope angle, and see if the slope angle is above 15 degrees. So say yes. If it is below, say no chance of lateral spreading. And L is basically distance to the river, how far a particular site is from the river. Closer, again, means higher chance of lateral spreading compared to being further away. So let's get going and let's code up our first decision tree model. So we're going to go to our website, which is AI in Geotech, and this should be in the description. So you should be able to click that and you should arrive at this AI in Geotech. All the materials should be available here. And let's go ahead, click on the decision tree example. And that's our decision tree. And you're going to see here like exercise and click on open in Colab. That allows you to launch a Colab interface for our notebook. We're going to be using a few different tools today, and you can trust this. This is my code and it should work. And I'm not trying to hijack your computer here. We're going to install a few tools like scikit-learn that allows us to do decision trees. Pandas is a very good data frame library. Gradient boosting allows us to do slightly more complicated decision tree models, and SHAP is how we are going to do all the explanations. This is a simple model, so we don't have to use a very heavy GPU. So just connect it with a very simple decision tree, CPU machine on Colab, and we should be good to go. Right, let me try to make it a little bigger so it's easier for you to watch. Okay, so here's our data. The first thing we're going to do is fetch the data, which is a CSV files of yes and no. So this is going to download that file, and that file should be available on the left. If we go here and refresh, after we have directly downloaded it, we've stored it in the data frame, so we should be able to see it here. So I'm only displaying the first 5 rows here, and you can see that there's a test ID, the groundwater depth, elevation, distance to the river, slope angle, pre-ground acceleration. This is the target. Targets where we're going to say yes to lateral spreading or no to lateral spreading. Okay, we want to drop a few of these features, which we are not going to use. Like I don't want test ID to be a feature that says whether or not particular site is lateral spreading. So let's remove that and also get rid of the elevation column. So we're only going to use these 4 features: groundwater depth, distance to the river, slope angle, and PGA to predict a particular site, which is yes or no to lateral spreading. All right, so first we need to create some training data, and then we are going to divide it into training, testing, and validation. This is important because I talked about whether we are interpolating and extrapolating or overfitting certain things. We want to make sure that we test our model in unseen data. So don't use all your data for your training. So keep aside about 15% of your data for your testing, about 5% for your validation to make sure that the model is actually working better. And then we will do all the evaluation in our test data. So here we're going to split it as 20% to testing and validation. So in that, I'm going to further split it into 15% for testing and 5% for validation. So we jumbled up the numbers here, meaning like each row got jumbled up. We didn't mix between the columns. And we now have a training data set, a testing data set, and a validation data set. So we can just run through to see that we have X test, which is the input for all the tests, and Y test is our target that we are interested in. So for example, site 578, the information of the test site, which we don't use, but we use all these 4 features here to be able to predict how well it does. Okay, let's code up our first decision tree. And the way decision tree is going to work, like I said, is find out a particular feature, and it is going to divide it up based on a particular value. So for example, if it looks at like slope angle, it's going to go through and see if a slope angle is about 15 degrees or not. And then if it is, it's going to say true or false. The way it splits is based on something called Gini impurity. And if the Gini value is 0, it means it's a perfect split. It's able to divide all the lateral spreading case from the no lateral spreading case. If the value is 0.5, then that means it's impure, meaning it is not able to do a good split. And this is the criteria that we are going to use to be able to split these data sets. All right, so the first step is import the sklearn scikit-learn library, and let's write our first machine learning model. Here we are going to do a classification tree. So we are saying it's CLF, and let me make it a little bit more bigger. And we write CLF, that's our variable that stores our decision tree. And we're going to import the decision tree from the scikit-learn library. And we're going to use a decision tree classifier. And here we're going to say the maximum depth of the decision tree is going to be 3, which basically means like the depth below the root node. So here we have depth of 2 from the root node, and we can say how deep our tree is. The deeper your tree, the more complex the division is going to be, and the better improvement in your accuracy, but don't go very deep because you can lose the idea of interpretability. So now that we've designed a decision tree, the next step is actually train it. And this is training our first neural network. And we are going to train it by using the command called fit. And fit allows us to say what data we want to train it on. These are the X input data. And then we want to make sure that we test it against the equivalent target, which is the Y train target as well. So once you do it, the training is going to run instantaneously like this. So the first step is create a decision tree, and then we are going to train it on X train and Y train. And there you go. The tree is ready, and it's almost ready, almost trained. That was incredibly fast because decision trees are really good at training, and we can see how well our tree did. Our tree on the training data set is able to do 65% of the cases correctly. Testing data set is roughly the same. So this is what you're looking for when you're doing a training and testing case, that they're roughly similar. So if your accuracy for training is 100% and your testing is like 80 or 70, then you probably overfitted your model or kind of starting to memorize what's in your training data a lot. So the accuracy score also gives you the same information, that we are able to see about 66% accuracy in our decision tree model. So let's now go ahead and do our first prediction. So we're going to make a test case. So let's look at the test case and probably look at the 5th row here. And let's also see what it does. So X test is 3271. I'm also going to look at what's going to happen for Y test as well. And then when we have Y test, let's see if we are able to predict for this side ID 3271, whether we are able to predict this particular side lateral spread or not. I don't know, because like each time this gets randomly created. So we are going to do our decision tree, which is CLF, classification tree, call the predict function, and we're going to call the predict function on the testing data set, which is X test. And the 4th row, we start counting from 0, 0, 0, 1, 2, 3, 4. So side 3271 is what we are interested in. So just to show you that this will print out the 4th row, let me do this. It is in pandas, so I probably need like ilog location 4 to say this is the 4th row of our data. So let's do our fit. So let's go ahead and train it, evaluate it. And we can look at the predictions here, and this is our prediction. Our prediction is that this side actually experienced lateral spreading. Yes, indeed, 3271 did experience lateral spreading, and you can see these are the features. So if you look here, it's pretty close to the river, 0.4 kilometers, 0.48 PGA, pretty high PGA, and the water table is under 2 meters below the groundwater depth. So that makes sense. Like I said, we should always visualize to see what is happening. So let's go ahead and visualize the decision tree. And here you can see that the first root node is a PGA. It's an impure split, so Gini impurity is pretty high. And you can see here, anything less than PGA, it says yes to lateral spreading, and anything higher than PGA of 0.42, it's saying no to lateral spreading. And then it might split again with PGA later on to say yes or no to these particular sites for classifications. We can, of course, increase the number of depth in our model. We used a depth of 3, so you should be, if we go back here from the root node, we should be able to count 1, 2, 3 to get to our decisions. Similarly, if I do a depth of 7, you can see that the accuracy shot up. We went from 66% to all the way to 75, 77%. So the deeper your tree, the more complex it would look like, and the better will be the accuracy. There are certain metrics that we could use to do classification. So some of them are called as accuracy. That is, how much of true positive and true negative did we get compared to all the predictions. Recall is how many true positives did we identify out of all positive data. Precision is true positive against all positive predictions as well. So if we look at some of these metrics here, we can plot a confusion matrix. And then let's go ahead and do that. And you want higher values in these cases. So the predicted is no and yes, and true value is yes and no. When they both match, that is, this is yes lateral spreading case, we want more values here. So our classification tree was getting 0.48 or 0.5 and 0.2. So about 70% of the model is predicting correctly, which is pretty good. 75% of the model predicting well. And this is on the training data set. You will get like slightly higher results typically. And we can also plot ROC curve. Receiver operating characteristics basically tells us what is the true positive rate. If it is a perfect model, it will go up all the way straight up here, and then it will stay flat. So if your area under this curve is actually 1, that means you have a very perfect fit. So we can do some of those and see precision recall, how they are doing. And more or less, this decision tree model has done reasonably well for us. You can also do more complex models like random forest or XGBoost. I'm going to leave that as an activity for you to try. I know we said no homeworks, but consider this as a special assignment. So what random forest does is basically, instead of using a single decision tree, it's going to use lots of decision trees and see, aggregate all the answers. And the good thing is, like, whenever you're averaging over multiple answers, they are actually better at giving those results. So you can use those, or you can use like XGBoost type models. But the drawback of random forest is you'll be able to, using hundreds of trees to answer it. So you will be able to only visualize one tree at a time and not the average or the whole behavior in a single go. But Dr. Ratchey used random forest in their prediction, and they did pretty well, achieving like really high accuracies in their model, reaching about 86, 89% accuracies. What we are interested is try to explain why we got these results. And this is why it is particularly interesting, because we can use SHAP values to understand how important individual features are and how are they going to affect our results. So SHAP allows us to say, what is the contribution of each feature? So we had 4 features: distance to the river, groundwater depth. We had peak ground acceleration and slope angle. We want to know how much each feature contributed to the result. So here we have an example where there are 3 employees in the company, and if all 3 of them work together, their total contribution is 100%. working individually, working in pairs. We have different effect on contributions, and we can do summation of their effect individually, in pairs, in groups, and evaluate on average what is their contribution. Although in this case, A only contributed 10 units by themselves, when you look at their overall contribution, a collective contribution as a group, A on an average did much better than B, even though B had a higher individual contribution. So going back to our example, we want to know whether peak ground acceleration or distance to the river, how much are they contributing in making our decision of lateral spreading yes or no. So here we can look at random forest and then look at the predictions. We use SHAP values to look at these. So what SHAP value says is like anything that is moving to the right is yes to lateral spreading. So distance to the river, it plays a big role. So the shorter the distance, the larger likelihood of lateral spreading. High PGA, again, larger likelihood of lateral spreading. Lower groundwater depth, contributing more towards lateral spreading as well. Then if you look at a case where there is no lateral spreading, in this case, only 7 out of 100 trees were saying yes to lateral spreading, compared to 90% of the trees, or 90 out of the 100 trees were saying this particular site actually lateral spread. So let's look at a case where there was no lateral spreading, and you can see that here, the groundwater depth is pretty deep, so close to 3 meters. Site is about 1 kilometer away, and all of that is influencing this site to be not lateral spreading. We are not only using the model to predict whether a particular site lateral spread or not, but instead we are explaining why the model is giving us this reason. I said these are black box models, so what we are doing is like looking post hoc, trying to explain what the result is. This is not the exactly how the model works, but there's kind of like an inferred understanding of how the model is behaving. But here's what things can get wrong. So it can learn something totally incorrect. Even when we go back and look at the decision tree that it learned, you may have noticed that when the PGA was below 0.4, it said yes to lateral spreading, and PGA above 0.4, it was saying no to lateral spreading. That was iffy, and you can see why that is the case here. It has learned something totally incorrect. In this particular site, it says this site will not experience lateral spreading because it has a very high PGA, whereas a site with a very low PGA of 0.37, or reasonably low PGA of 0.37, it's indicating that has a higher probability of lateral spreading. So that puzzled us. So we wanted to understand why this was happening. And you can see here that it learned certain sites which had very high PGAs in these regions did not actually experience lateral spreading. This could be clay sites or rocky sites in a particular area which did not experience liquefaction and further lateral spread, meant the model learned something totally incorrect. And that's very critical when we are trying to build machine learning models, because it is based on the data and it can learn completely incorrect aspects. So this bad relationship happened because we had extremely high PGAs on the right bottom corner. So probably like southeast corner here, where you had like really high PGAs, and these regions did not experience any lateral spreading, resulting in our model learning something totally incorrect. All right, so that was a very simple machine learning model. So now we are going to switch gears and see how we can code up our own multi-layer perceptron, our artificial neural network, and see if we are able to do any better. And then we will start putting some physics into our simulations and see how they go. All right. So what is a multi-layer perceptron? This is also called as artificial neural networks in the 1990s. And since the 2007s, these are called neurons, or a collection of them is called like a multi-layer perceptron. So what you're seeing here is a single perceptron, which basically takes multiple inputs as the arguments, and it's going to do some sort of linear transformation. What we mean is like you have X as your input feature values. We're going to multiply it by a weight matrix, so a literal linear transformation with a bias term B. So that's the first step. A perceptron basically takes your input, does a linear transformation, adds a bias, so shifts your transformation up or down, and then we pass it through a nonlinear activation function. We need some sort of nonlinearity to model most of our complex physics, but essentially a perceptron is just that. You have a linear transformation followed by a nonlinear activation function. That's it. Put lots of them together and you have a multi-layer perceptron itself, and that's a artificial neural network. And this is extremely powerful because what a multi-layer perceptron can do, even a single layer one, is that it is able to approximate any continuous function as long as you're wide enough in your neural network. This simple linear transformation followed by a nonlinear activation is what's revolutionizing our world. Why do we need nonlinearity? We have most of our functions to be nonlinear, but we need some sort of control where we want to be able to split and understand nonlinearity. So here we're going to look at an example where I'm going to do a classification problem. So let's say I'm in this input space where I have two feature space, X1 and X2, and I want to be able to separate out the orange and the purple classes. So think of it as our yes and no lateral spreading classes. And what we are going to do is a linear transformation. So multiply W transpose times X. So W is our weight matrix. So if you think W is a scaling one, it can just like expand our contract. If you want to look at the map, this is how it does. So our scaling factor means it just scales how big our weight matrix is. Or you can think of it as a rotation matrix, which is cosine and sine theta. And you can rotate your input space. So here you can see that you can either rotate it or you can scale it up. But that's not very helpful because I'm still unable to separate the orange class from the purple class. Whereas when you set the nonlinear activation like ReLU basically means no matter what your input is, if your input space is negative, there is no output. And if your input space is positive, there is a positively incremental output. If you look at sigmoid and tanh, they are saturated activation functions, meaning their values will never go above 0 and 1 here for sigmoid, or -1 to 1 in tanh functions. So let's go ahead and set up the ReLU function where I say the negative value should be 0 rather than a leaky ReLU, which allows some negative values. We can see that it's starting to cluster together. Maybe there is an angle at which I will be able to separate out the yellow classes from the purple ones. So you can see here, I'm almost there, but let's go click solve. And it found out an angle that is the rotation matrix W with a corresponding scaling factor that allows me to separate what I couldn't do in the input feature space. I was able to do it in the nonlinear transform space. So this is a single perceptron, which is basically does a linear transformation followed by a nonlinear activation function, and I'm able to separate out those two classes. So that worked very well for us. So why don't we try and use this MLP in our approach? So let's go ahead and build a multi-layer perceptron and see how that works. So multi-layer perceptron is take the single perceptron. Instead of having one perceptron, we are going to have a lot of them. This MLP has 3 input features and 1 hidden layer. So this is what we call as the hidden layer, and the output layer is on the right-hand side. The multi-layer perceptron allows you to combine these inputs, do your linear transformation followed by a nonlinear activation function, and get out as these outputs as well. So the next step is to figure out whether what is a good loss value. because unlike a classifier which says yes or no, we now have a multi-layer perceptron which outputs a continuous function. So we need to be able to say whether a particular value is no liquefaction or no lateral spreading or lateral spreading based on a value. So if our value is always bounded between 0 and 1, we can say any value below 0.5, it's called as, let's call that as no lateral spreading. Any values above 0.5, let's call that as lateral spreading. So in order to define a loss, we're going to use something called as binary cross entropy, which tells us how much to punish basically the wrong predictions in our model by giving it some confidence in its output. So here, if you see here, as I change the model's outputs, the confidence of it changes, but it's starting to punish different values differently to be able to segregate sites which were lateral spreading through sites which did not. So if I show the optimal here, you can see that they have very low Y values and be able to separate out very well the correct prediction from the incorrect predictions. So that's great. So let's now that we have a loss function, we need to be able to optimize it. We optimize it using something called automatic differentiation. Automatic differentiation takes two input x1 and x2. We are going to define a simple function called y equals x1 squared plus x2. We build out a graph. And the way we build out this graph is set out all the operations. So we have x1, we have x2, square x1, add it up, and you have your output y. So what you do here is just pass in the value of x1 and x2, and we get out the value of y equals 7. What are we trying to do here is like try to minimize the loss which we defined before. The way we would normally define a loss is take the gradient of the loss with respect to the input parameters. So what I'm trying to do here, instead of doing a finite difference, is to set up something called a reverse mode differentiation, which allows me to compute the derivative of the problem with respect to our inputs. So taking the derivative of our loss with respect to our inputs. So here I'm taking the derivative of y with respect to x1 and x2. So what happens in reverse mode AD, this is what is called as backpropagation in machine learning or MLPs, is that we create this computational graph and then we pre-compute what is the gradient of this node with respect to the next one. So here, for example, the gradient of node y with respect to W4 gets computed. The gradient of then W4 with respect to W3 can be pre-computed. So this gradient is, what is the gradient of W4 with respect to W3? That's just 1. That gets stored here. Gradient of W3, which is basically W1 squared, which is squaring x1 here. If we take the derivative with respect to x1 or W1, that is 2 times W1. So all of these terms get pre-computed, and because each node connects to the next one through an edge, we can store the derivative along the edge. Why do we do this? So that when we have a function y equals x1 squared plus x2, we can basically go in and write out those derivatives here and say, what is the derivative of y with respect to x1? I follow along this chain, do a chain rule, which is multiply every derivative I have along that entire chain. And that is 1 times 1 times 2w1. W1, the input in this case is 2, so my gradient is 2 times 2, which is 4. The gradient with respect to y with respect to x2 is basically 1 times 1. That is the gradient here, which is 1. The important thing to note is, unlike finite difference, your gradients here are exact. It can be almost pre-computed, so they're incredibly fast. And this is what is called as the backpropagation, and that powers most of machine learning today. So how machine learning works is basically initialize the weights randomly, and we're going to loop until convergence, compute the gradient of your loss with respect to the weights, which are the parameters, the weight matrix W, and the bias term B we had in our MLP. We're going to optimize with respect to those. update those parameters until we get a solution where we have an acceptable loss value. We are going to use a stochastic gradient descent algorithm that allows us to find the global minima, ideally the global minima, and that depends quite a lot on how we set up our problem. So here, if you use like really high learning rates, you can jump around and get stuck. Or if you use like really small learning rates, it never reaches full convergence. But if you reach an optimal learning rate, for example, here you can see that it's able to find the right slope and get to the solution very nicely. So we have all the ingredients for our machine learning model. We are able to uh, find the loss, binary cross entropy, define our neural network, and we want to make sure that we do not overfit our model. This is what we would call as overfitting, is when your model is extremely complex and you're trying to fit every little noise in your data. We are going to evaluate how well our MLP does and then see what we can identify. So let's go back here and then go to the MLP section, and you're going to open up the exercise again. And let's code up our first artificial neural network, or MLP. So you should be able to see all the outputs and what the definitions of these functions are. So let me go ahead, run them to show how our activation functions look like. So we can see them. Again, this is going to be a slightly smaller problem, so we don't need like an extreme amount of GPU or compute to do. The MLP we're going to build first is to try out what automatic differentiation would look like. So here is the same AD demo that I did before. So I'm doing x1 squared plus x2. But in order to get automatic differentiation, all we need to do to compute the gradient is y, which is the output, and do y dot backward. And that's it. And then after that, you can get your gradient with respect to x1 and x2, which was 4 and 1. And we got exactly the same result here. And this is how we're going to build a simple neural network. So we have a simple neural net where we're going to take two inputs, and there's going to be three hidden layers, and then that's going to be one output layer as well. So the first step is to say neural network dot linear, and then we're going to take in the input, which is two input features and three output features. Those output features are going to be to the first neural network hidden layer. So three hidden layers and one output here as well. So once we have that ready, we have our first neural network coded up. We use the first layer has a ReLU activation function after this linear layer, and then we use a sigmoid activation function, so our values are going to be bounded between 0 and 1. And if I take x as the input, which is 2, 1, and 2, and y true is this value, we can go ahead and make our prediction. So let's go ahead do this. So we've defined our network as net here, and it's going to take the input x, and then we are going to see what that prediction is. Again, we have not trained it yet, so there won't be any correct prediction, or hopefully no correct predictions. And we are going to define the binary cross entropy loss, because we are doing a classification problem to take both the y prediction and y true values to look at the classification loss. So the loss, this is where we're going to do the automatic differentiation. So here we are going to do loss dot backward to compute all those gradients. So here we're not doing much. We are making a simple prediction. The prediction is 0.3706. The target is 1, so we are way off. Of course, we haven't trained this neural network. And that's what this says. Your loss function is pretty high, and these gives us the gradient, which allows us to do the training in our next step. let's go ahead and create our first gradient descent training, which is our MLP to do the same problem that we did the classification on. Import the data. Let's go ahead, install PyTorch, get our data. This is the same data we used to do our classification problem. Do some of the cleanups so we can split it, look at the distributions of your data, and then eventually split the data into training and testing. So I'll give you time. These notebooks are available, so you can go through and see how we split the training and testing data sets. Then we go ahead, build our own neural networks. This is a slightly complex one to what we built, but we write it as a for loop so that it makes it able to build with 4 input features. So the groundwater depth, distance to the river, peak ground acceleration, and slope, and output 1 value, yes or no. And since this is a binary classification, values below 0.5 is going to be no, values above 0.5 is going to be yes to lateral spreading. So we use sigmoid, and you may have seen the sigmoid activation function, which basically goes between 0 and 1. So this is false, this is true, somewhere between is where we split. Okay, so we have our model, and we're going to look at the model. Can take input features as 4. There's a 64 layer hidden, 1 single layer with 64 neurons as the hidden layer. ReLU activation for both of them. Finally, sigmoid because we're doing classification. That gives us 1 output, and we're going to make a prediction, evaluate the loss, backpropagate it, and then use the optimizer to update the gradient of our model, which is the weights and biases that we've been talking about, and then see how well the model works. This is going to be slightly slower because compared to the classification example, but this allows us to see what's happening. So here we are doing it to 1,000 epoch. 1 epoch is basically me going through the entire training data set once. So I'm saying go through that 1,000 times the entire training data set, and our accuracy is about 76%. That's about the decision tree with 7 layers deep. And if you plot the cross entropy loss, we want to make sure that it didn't overfit. Just going back to show you, overfitting would mean like your training data keeps decreasing in loss, and your testing data loss keeps going up. You're essentially doing this in this case. You want to make sure that both of them uniformly decrease together. In this case, that happens very well. You can see a nice decrease, and that allows us to say, okay, that's a good model. Let's run some predictions. Again, pretty good accuracy, about 75% for a simple model. But one of the interesting things is that the deeper your model becomes, the more accurate your model predictions would be. I think I'm probably missing some lines. So let's look at some of the results here, where we want to compare the ROC curves, and here you can see that it does a reasonably good ROC. Area under curve is 0.8. You want 1 is like perfect. We can never get something perfect. So it does something really well. And then we can try different sized parameters. So instead of using 64 neurons, you can add more layers. You can increase the number of neurons in your deep neural network, or increase the number of layers in your neural network. That's called a deep neural network. That means that the smaller models have lower accuracy. Larger models, as I said, become more complex, and they achieve higher and higher accuracies for classification. None of this actually incorporate any physics in the model. There's no underlying physics that goes into these outputs. But I want to very quickly show you how we can incorporate physics into machine learning. This work kind of started with Razy et al. And George Kanadakis when they came up with the idea of physics-informed neural networks. I'll show you a quick example, and let's walk through a 1D consolidation problem. So let's say there is a damped harmonic oscillator. I'll show you what that looks like. So our PINN oscillator is here, and we are going to play around and look at our damped harmonic oscillator. It is a mass attached to a spring, and then it does oscillations like these. What we're going to do is do a purely data-driven approach to fitting these model, and then see how well our neural network is going to approximate this function. Then we will do a physics-informed approach and see how that does. Okay. So we have this particular ordinary differential equation, which is based on time. So mass times your displacement derivative, which is respected twice, damping coefficient with respect to velocity, and stiffness times your displacement equation. A traditional data-driven model would mean like I would take time as the input and I would try to predict what is the displacement at any given time t. In this case, you see a two hidden layer neural network, which you know to the right. Instead, we use tan H instead of all the ReLU or sigmoid activation functions. When I tried to fit, I used these 10 data points. These are the measurements I had, and I tried to fit that model. And you can see that it does very well whenever I'm trying to interpolate. And this is the problem I've been highlighting. Like when you try to extrapolate and go outside your training range, your model will fail catastrophically. And the problem is we never know when we are outside our training range. And here you can see it works very well, and you're confident it's working, and suddenly it's deviating completely away from it because it has no data on which to train on. So what if we know what the underlying differential equation is? In this case, we do know what the ODE is, and can we somehow incorporate that differential equation into our problem? So let's go look at how that will work. In order to do that, we have the exact same neural network, the neural network which takes in time as an input and outputs the displacement at a given time t. But what do I need to do if I want to solve or satisfy this differential equation? If I need to satisfy this differential equation, I need to take the derivative of u with respect to time once and with respect to time twice so that I can fit it into this residual equation. So I know this PDE needs to be satisfied by this displacement output. So I can just use u directly here for the stiffness, but I need to be able to calculate the derivative of u with respect to time, derivative of u with respect to dt squared. How can we do this? And this is where we go back and say, we know exactly how we do it because we've been talking about automatic differentiation. This looks exactly like AD workflow where I have set up a graph, I calculate the output, and whenever I do output dot backward, I'm able to get the derivative of the output with respect to the input. That's what AD was. That's what the backpropagation was. So why don't I do that for physics? So I know what the output is. I can go here and set up the derivative of u with respect to time t, take the derivative of this output with respect to time t again, and voila, you have actually satisfied the differential equation. And that's it. So physics-informed neural networks is very simple in a sense that all you need to do is add the underlying PDE as a loss function. We have the power of automatic differentiation to give you that derivative which you need to satisfy your PDE, add that to your data loss, or sometimes you can do it without the data loss, and you will be able to satisfy the differential equation with some caveats. We need to evaluate these derivatives, and the way we could do it is basically do torch, which is because you're using PyTorch, automatic gradient or automatic differentiation, take the derivative of u with respect to time, take the derivative of du over dt with respect to time again, and you will be able to satisfy the residual equation, which is mass times your acceleration, damping coefficient times your velocity plus stiffness times u. That's your loss in addition to your data loss. So if we do this, and we are going to do this at something called as the co-location points. So I discretize the entire simulation time 0 to t into 200 points and ask it to evaluate the PDE loss at these 200 locations. By saying like we can evaluate at these 200 locations, you can satisfy what the PINN's loss function would look like and satisfy both the data and the PDE loss. So if I train the neural network, this is going to be slightly slower. But if we do that, you can see the red line here not only matches the data, but does pretty well for the rest of the system. Whereas the standard neural networks try to diverge beyond the training data, our PINN's network, which has the underlying PDE, is able to match the exact result really well. And you can see that here much more better that the PINN's system is able to recover the phase portrait very, very well. So, okay, we now have an idea of like how PINNs work. So we'll take the last 5-10 minutes to look at a 1D consolidation example. It's a very geotechy example. We have the Terzaghis 1D solution, and let's look at if PINNs can solve this problem as well. So what do we need? First, we need the differential equation. So I have a soil sample of height h. I'm going to apply a surcharge at the top. This is fully saturated. And we're going to look at how these isochrones are going to develop, how consolidation is going to happen, with top to be draining, bottom to be impervious. That allows no drainage at the bottom. This is the differential equation we need to satisfy, but now we realize our differential equation needs to satisfy both the derivative with respect to time as well as space. So z here is the space. We need to take the second derivative with respect to space and the first derivative with respect to time, put it in these differential equation and solve both the data loss, the physics loss, and we have certain boundary conditions like the top is draining boundary, so we want the pore pressure to be 0, and bottom is a no flow boundary condition, and we want to take the pore pressure output with respect to space, and that there is no velocity or no flow in that condition. Okay, so what we're going to do is we need to say where are we going to satisfy this PDE, and because it's both on time and space, we want to make sure that we can do it vertically in terms of space and time. I'm going to roll that out in time, and for the entire duration of our simulation, I'm going to have co-location points where I satisfy this PDE. All right, so let's go ahead and look at how that would look like. So let's go to our problem here and do PINN's 1D consolidation and open up the exercise here. This we can ask for a GPU because PINNs is going to be computationally intensive. So let's go ahead and request a GPU. Hopefully Google will be nice and give us a nice T4 GPU. And I have most of the code written, so the stuff we're going to do is just computing the derivatives and making sure that we write out the residual. And I'll show you a simpler one, and then we can do a complicated one as the no homework. Okay, so let's scroll down to where we have our gradients. So we can say anytime you want to compute the gradient, we're going to use torch.autograd.grad. So if you want to take the gradient of u with respect to z, so this is the spatial derivative du over dz. And if I want to take the derivative of time, it is going to be du over dt. So we can see that our network is quite complex. So we have 5 hidden layers, 2 inputs, spatial dimension, so where we are located, and time dimension. And we're going to say what is the pore pressure at a given space at a given time. And we need to take the derivative with respect to time. double derivative with respect to space so we can satisfy the underlying PDE. So we're going to do this with a simple network, and then we can make it more complex. So let's, first thing is calculating the gradients. So let's do the first derivative. So we're going to calculate the derivative of u. Sorry, Google's being extremely helpful. And we're going to take the derivative with respect to time. And one thing we need to do is making sure that the output size is defined. So that's what we're going to do here is we're saying the derivative is going to have a size of u. And this we need to make sure the automatic differentiation graph is set up correctly and is continued so that we can take derivative again as well. So this allows us to calculate the derivative of u with respect to z and t. So I have concatenated both z and t, so that allows me to do zt as a variable and take the first output, which is with respect to space, second output with respect to time. Now we are going to take the gradient of uz, which is this variable here, and I want to the double derivative with respect to space. And so this is going to be, again, zt, and we will extract out. The outputs should look like ones like, and in this case, they need to look like uz. So that's the size we are interested in, and we need to make sure that the graph is created, and we'll want the first output from there. I need to fix my typo here, which is harsh.once. All right, so that allows us to compute the derivatives, and we know the PDE looks like this. So du over dt is cv, d squared u over dz squared, and we want to define a residual, and a residual should be always equal to 0. So we need to define, take the du over dt term to the right-hand side, or the right-hand side terms to the left, so everything becomes equal to 0, and then say minus cv times uzz, which is our second derivative. So now go ahead and click on run. So one thing you would notice is that the PINN's training is going to take a while. This is going to take about like a minute and a half, and I'm using something called Atom, which is like a momentum-based optimizer, which helps me to do a little better. And then we'll come back. So it should take about 2 to 3 minutes to run. And you can see the physics loss is quite high. It's decreasing initially. And this is the boundary condition loss, loss at the bottom. And this is the initial condition loss values. So I have the results already, since that's going to take a couple of minutes to run. Let's go ahead and look how those would look like. So here you can see that the analytical solution matches really well against the PINN solution. There's some deviation for the initial times, but PINNs is able to do reasonably well. The reason why it was able to do a reasonably good job is because we were actually using 2 optimizers in that example. This one will take definitely like 2 hours to run, so I wouldn't recommend you to run it right now with me. But we have the results stored, and you will be able to fetch those or even get the trained models and see that we got really nice loss functions with initially with Atom and a second order optimizer called LBFGS that gave a very good isochrones for us. So yes, we can put physics into the neural networks, but one important caution is please don't use physics-informed neural networks to do forward problems. If you haven't yet figured out why, it takes incredibly long time to do. There are other approaches like operator learning, which are better when your boundary condition changes, geometry keeps the same, but your function changes, your forcing function changes. those results change. Whereas pins is fixed for a given geometry, given boundary condition. You're solving the whole problem. This is computationally intensive. Traditional numerical methods generally do very, very well for these problems. We've been building it since the 1970s. So always use that in making those results. So we got reasonable results here. If we train it more, add more values, like I said, like we need a second order method, we will be able to improve on those results. So never use pins for forward problems. So you might ask, why are we talking about it then? The important aspect is they are actually good to incorporate physics. And if you're doing state estimation, let's say you don't know what your CV is, but you have measurements, you will be able to use pins to do inverse problems. Pins are only useful when you're doing inverse problems, so please don't try to apply pins, not just in geotech, but in general, pins for forward is a bad idea. Methods like operator learning, DeepONet, our own basis to basis, and function encoders are much better because they do function space to function space mapping, which means you can change your boundary conditions, change your loading conditions, and see how your results would vary. So want to show few other applications that we haven't seen, but there is a whole world of exciting possibilities of AI and machine learning. There's, of course, graph neural nets, which are able to completely replicate what your high fidelity simulators are doing. We have open source codes available from our group under GeoElements. And you also can do CNNs to do seismic inversion type problems, which are done quite a lot by Dr. Joe Van Tassel at Virginia Tech and also Dr. Brady Cox at Utah State. And we've worked together on several of these problems to do seismic inversion. Are everyone's favorite, ChatGPT. There's lots of agentic tools. I have a video of me talking about agentic LLMs also on the ASCE GI Pi Day. So please check that out if you want to see more about agentic LLMs. Our generative AIs, we can actually go from images or text to basically building 3D models and testing those 3D models in our simulator in a matter of minutes. So that's an exciting world of possibilities for AI and machine learning. So I hope you enjoyed this little very brisk breakneck speed tutorial on how to do machine learning with geotechnical engineering. Please don't forget to check out our online course. Again, I'll leave that here for the QR code. It's available here, should be also in the description. If you have interest to do more around AI and civil engineering, we have our NSF funded center, Chishiki AI, the lead PI for that, where we develop a lot of courses, tutorials, materials for AI and geotechnical engineering, and we also have fellowships for researchers working in AI and geotech. I hope you had a fun time learning about AI in machine learning and geotechnical engineering. Thanks for listening in on the summer school.